second lecture. In the first lecture, as you probably recall, Marika gave us an introduction to ADC, the general introduction. Now she'll start talking about getting closer to her own work. So I'll do this as well. And I wanted to emphasize just the format is very flexible and informal, so of course you're very welcome to ask questions at any point during the lecture. So that's the whole point of our being here. So please interact more. Okay, so thank you very much.
Okay, so indeed, I'm going to talk about aspects of entanglement. So the basic reason seems very disconnected from what I was discussing last time, but over the past few years we've realized that there are very deep connections between entanglement, which up to maybe 10 years ago had been mostly considered in the community working on quantum information and condensed matter. It hadn't been so much thought about by the high energy community. But there are deep connections between entanglement, quantum field theory. So we realize that entanglement is also interesting for understanding aspects of quantum field theory, such as renormalization group flow, and holography, connections to black holes and quantum gravity. So to some extent, the connection between entanglement and black holes, had come beforehand, but this has sharpened a lot over the last 5 or 10 years. So references for this talk. So when I was preparing this talk, I realized that there are 6 sort of published papers and about another 5 in progress on entanglement. And so it's not really realistic to talk about all of them, and nor is it probably sensible to kind of, jump from one to another, because some of them are quite different topics. So what I'm really going to do is concentrate on a couple of them, and then towards the end, I will tell you about the contents of the other papers. And people are very welcome to come and talk to me about that. I'm here for another couple of days if you want to hear more about those papers. So in particular, I would anticipate that this paper about massive flavors is an interest to you. Okay. And this, I should say, I'm also very happy to talk about it. It has some connections with the recent discussions on complexity. So I won't discuss it so much here, but I'm happy to talk in private. Okay, so what I'm going to do is start with a sort of, again, a rather biased introduction to entanglement entropy, but just sort of setting the scene before I move on to why holography is a really interesting way to talk about entanglement entropy. So I'm going to start, with really, going back to quantum mechanics 3. So maybe you in Mexico would cover this in your quantum mechanics courses, but we actually really don't in the UK. We just about get to density matrices, but we don't really do much with them. So we have a system which is described by a density matrix. It might be a reduced density matrix in the sense that I give you a density matrix and I've traced out some degrees of freedom. But in any case, I give you a density matrix. Then you can compute, associated with this density matrix, a von Neumann entropy with a standard formula, trace of rho log rho minus trace of rho log rho. And so in the context that we have defined our density matrix by tracing over some degrees of freedom, it's a reduced density matrix, we can interpret this von Neumann entropy in terms of an entanglement entropy. And really for the purposes of almost everything I say today, the kind of setup that we're interested in is a case where we've got a Hilbert space which can factorize into a product of 2 Hilbert spaces. And now we've defined our reduced density matrix by tracing over the degrees of freedom of the second part of the Hilbert space of our original density matrix rho. And I should say, the density matrix for the whole system, it could represent something that's pure, it could represent something that's mixed. But if the original density matrix for the whole system is pure, there's a complementarity property, which will play a role a little bit later, that if you trace over A and, if you trace over B and get rho A, the reduced density matrix, after integrating out the degrees of freedom of B, and you compute its entropy, and then if you do the converse, you trace out the degrees of freedom of A, and then compute the entanglement entropy associated with rho B, these must be equal if the original state was a pure state. Now, if you want to sort of think of a nice example on this, you can just think of, and in some sense, the arena in which this has been most used is in the arena of quantum information, where people are talking about qubits. So the simplest qubit system is indeed, just a single qubit. To get something non-trivial happening, we need to take 2 qubits. So we consider a 2-qubit system, And let's suppose that we have such a system which is in a pure state. And here I should say that, the 0, 1 indicate up and down spin states. I switched to notation 0, 1 because I'm really thinking in terms of, a quantum information language, a qubit kind of language, but it would just be spin up, spin down. And the notation here indicates the state of the first spin and the state of the second spin and so on. Okay, now, if you construct your density matrix in the standard way and you trace over the second spin, you produce a reduced density matrix rho A. It's manifestly not no longer representing something which is pure. It doesn't satisfy the requirement for the density matrix to be pure. And thus, if you go ahead and compute the entanglement entropy, the von Neumann entropy associated with this density matrix, so you really just brute force plug into this formula over here, you'll find that the entanglement entropy you get is log 2. And in this case, I did a trace over the second spin, but the original state was pure. So if I traced over the first spin instead, and I computed the associated entanglement entropy, again, I would have come up with the answer log 2. Now, what is the significance of log 2? The significance of log 2 is in terms of the physical interpretation. So the entanglement entropy is essentially counting the number of entangled bits between the two systems, A and B. Or another way of saying this is that if you take the entanglement entropy and you exponentiate it, that's the minimal number of auxiliary states you need to purify your density matrix. And so in the case at hand, we exponentiate log 2, we get 2. So the minimal number of auxiliary states that we need to purify rho A is 2, but that's indeed exactly what we started from, right? So we started with that. Okay. And so if one wants to think about interpretation of entanglement entropy, it's really these two things that I've highlighted here, which is a useful physical way of thinking of the interpretation. Okay, now entanglement entropy in these sort of toy systems, so 2-spin systems, 3-qubit systems, it's you can play nice games in quantum mechanics. I said we don't teach this in the UK, but actually I often have bachelor's projects in the sort of third year of undergraduate playing with this kind of thing and looking at Bell states and entangled states and so on. But it's there's nice games you can play, but it's reasonably straightforward. However, in the context of a real quantum information system, we will, ultimately be interested in describing quantum computers with a large number of degrees of freedom. And so we really, will not want to work with techniques which just involve a small discrete number of freedoms, degrees of freedom. So we won't be 2 or 3 qubit systems. At the moment, quantum computers are limited to, say, something like 20 atoms. But of course, the goal ultimately is to have very large systems. And so we need to develop techniques to actually understand entanglement in systems with more degrees of freedom. Okay, now in quantum information, there are many other measures of entanglement that are used. And if you go to a book such as Nielsen and Chuang, the famous book on quantum information and quantum computing, you can find many other measures of entanglement. I mean, the string theory community has had fun over the last 5 years or so, in a sense, taking that book and trying to take those concepts and see if they can realize them in holographic systems. So there are many measures of entanglement. And so in particular, somebody could have already, in a sense, complained. I took a Hilbert space and I partitioned it into 2. And you could have said to me, well, why didn't you partition it into 3 or into 4? And look at the entanglement between the 3 parts of the Hilbert space or the 4 parts of the Hilbert space. And indeed, if you go to quantum information literature, there's considerable discussion of measures of, say, tripartite entanglement entropy. Tripartite entanglement. Entanglement entropy, however, has some rather special features. It's really the most robust measure. Robust in the sense that we make local unitary transformations and it is preserved. And it's a measure which is additive in a sense that's very useful for us. So in particular, if you take a density matrix which is a direct product, the entanglement entropy is just the direct sum. So it satisfies many useful and important properties. Many of the important properties are not going to play a role for this particular talk, but it's definitely a quantity which is singled out as having the nicest properties of the measures of entanglement that people have written down.
You know, in the tripartite case, is there absolutely no preferred measure? Is it completely up in the air, or is there some?
There are various candidates, and they capture different features. There are issues of robustness in the sense that you make, say, unitary transformations with some of the candidates. So I think it's somewhere in between. You know, that there are measures, but they don't have the same, nice, clean properties that this has. I should say, actually, I have a master's student who's working on this, so we can talk about that too. Okay, now, as I was saying, in a sort of, we want to use the entanglement entropy ultimately for a quantum computing system. And so, really what we're interested in there is probably going to be entanglement between different regions of our system. So this would be regions of our computer hard disk. The entanglement between a region A and a region B. So we can illustrate this in the context of a one-dimensional spin chain. It's not an accident I show this example, because this one spatial dimensional spin chain, so two-dimensional description when you include time, is perhaps the most studied in the condensed matter literature. And so in such a spin chain, the natural thing to do is to divide it into two parts, sort of A and B. I should say I've shown them here as sort of semi-infinite, so A is to the left and B is to the right, but we could have more complicated regions than that. And similarly, in a quantum field theory, again, perhaps the most natural thing to do is to think of your systems as being defined in terms of subregions of space. So again, we've got a two spatial dimensional quantum field theory here. And I've taken my two spatial dimensions and I've just divided it into two, so a region B and a region A. And for most of this talk, this is the entanglement entropy that I'm interested in. So I call it, perhaps, misleadingly, because I'm going to go to a holographic description later, but it's what the quantum information community might call a geometric entanglement entropy, in that the division of systems A and B is based on the geometry. Now, this system here, as I said, has attracted a lot of interest in the condensed matter community, really over the last probably 20 years. And one of the features is that, why I picked out spin chains in particular is that many of the spin chain systems that people are interested in condensed matter have integrability properties. And then people can actually go ahead and calculate the entanglement entropy using the underlying integrability of the system. And what people found was that if you look at ground states in systems with a gap, so there's some mass gap of the excitations, typically what happens is that the entanglement entropy scales with the area of the boundary between A and B. Now, in the one-dimensional case that I've shown here, the area, the area of the boundary is zero-dimensional, right? It's a collection of points. So we really just say that the entropy is a discrete number. It's perhaps better illustrated in a two-dimensional system. So we're saying that the entanglement entropy scales with in this case, the length of the boundary of the region A, the region B. And there's a good intuitive reason for why that is. It's saying that you have a local description. You have local interactions in your system, and entanglement between pairs at the boundaries is the dominant feature. So we're in a gap system. So if we calculate the correlation functions, they between degrees of freedom, they fall off quite rapidly with distance. And so the dominant contribution is really from pairs of spins which are actually separated by the boundary. Okay. Now, in the case that we have what condensed matter physicists would call a quantum critical theory, or what we as people as high energy theorists would call a conformal field theory. So if you take something which is one space dimensional, one time dimensional, two space time dimensional, quantum critical theory, a conformal field theory, very famously Halsey, Larson and Wilczek about 20 years ago showed that the entanglement entropy in the ground state behaves logarithmically with the width of the entangling region. And the prefactor here of this log is the central charge of the two-dimensional conformal field theory, which I mentioned the other day. So we also understand the central charge in terms of the trace of the stress tensor of the conformal field theory when you put it on a curved background. The central charge C also shows up in the two-point function of the stress energy tensor. So it's the defining feature of the conformal field theory, which counts the number of degrees of freedom of the conformal field theory. But now L is a quantity which has a length, and so to form a logarithmic quantity, we need to get something dimensionless, we will need to have another parameter. So what is the parameter? So it scales as log L over epsilon, where epsilon is interpreted as the lattice spacing in the underlying discrete system. And so let's pause here and sort of think about what people do as a condensed matter physicist. So you're interested in some system which is essentially discrete. So you have in mind some system, of atoms, and there is some discrete description, and you use quantum field theory, continuum quantum field theory, as a tool to explain what is going on in your discrete system. And so, if you look at papers on entanglement entropy from the condensed matter community, so people like my former colleague in Amsterdam, Pasquale Calabresi, we overlapped for many years in Amsterdam, John Cardy, they will actually often do the calculation using integrability techniques. So they use a discrete system. They will use conformal field theory calculations, and they will actually show you graphs to convince you that they actually match. So they're using the quantum field theory as a tool, but they're really interested in an underlying discrete system. And so for them, the cutoff that they use, the parameter that will come in, will always be the lattice spacing of the underlying system. Sorry, I'm going to move that out of its way. Okay. Now, if we think about what happens in general dimensions, and we look at conformal field theories, so now we're in a quantum critical conformal field theory in d plus 1 dimensions. D is the number of spatial dimensions. Little d is d plus 1. Then we already argued on very general grounds that in a ground state we might expect there to be a contribution to the entanglement entropy, which is associated with entanglement between degrees of freedom that are separated by the boundary. And this would scale as the area of the boundary. So for simply because I'm not good at drawing, and also because later on I will be interested in two spatial dimensions. Here, I'm almost always showing a picture in which my boundary is actually one-dimensional, so my area collapses to be a length. But in general, it would be a higher dimensional surface, and it's just the area of that boundary. But again, entanglement entropy is a dimensionless quantity, and so that area which is dimensionful must actually come equipped with certain powers of a lattice spacing. And you just count it up, and the power you need is d minus 1. And if we go, so that's the leading term in the entanglement entropy. That's the leading entanglement. But in higher dimensions, as well as in 2 dimensions, we actually find sub-leading contributions. So now if you look at what happens in a 2-dimensional conformal field theory, you can see that this term here, as we said, it collapses to just be, it would just collapse into a term which is just scaling as epsilon to the 0, and so it effectively can be absorbed into the log term. So in higher dimensional cases, you have this term, which is a power law, which is the leading term. But you also, just as you had in 2-dimensional conformal field theories, you get a log divergence. And now the log divergence scales with the scale of the region A. So it scales as the width of the region A. And again, it appears with the power of the cutoff. And the coefficient A is again related to the coefficient of the trace anomaly. So this is a trace anomaly for odd spatial dimensions, even space-time dimensional conformal field theories. Now, as you go up in dimension, there are various types of anomalies that you can get for the stress tensor, and it turns out that the anomaly which plays a role here, and the anomaly which indeed plays a role in candidate generalizations of Zamolodchikov's theorems, is the so-called A anomaly of the stress tensor, and that's why I use this notation. Okay, so you get both a power law divergence and a log divergence. Now, why do people calculate this in quantum information condensed matter theory? Well, actually, there are a number of different reasons. So one is that ultimately the problem people are often interested in solving in quantum information condensed matter systems is they've got some Hamiltonian of the system, and they want to know what is the ground state. And so the entanglement entropy is a tool that is used in trying to find efficiently the ground state wave functions. So it's related to matrix product state ansatzes and so on. So it's something which comes in very naturally there. The other thing is that we've already seen in what I say here, a distinct behavior between a gapped system and a system which is quantum critical. So there's a distinct behavior in the entanglement entropy which characterizes different phases of the system. So you do this calculation and it gives you information about the phases of the theory. And then the other thing which I put in a question mark here is that, entanglement entropy is something that people also discuss measuring, at least in small cold atom systems. So the kind of toy quantum computers that people have in the lab, it's often a small number of atoms. People look at ways of actually trying to measure this quantity. Okay, that's an interesting discussion in itself. It's sort of, okay, so why is it an interesting discussion? If you have a very small number of atoms, it's effectively quite easy to make a series of measurements which determine as much as you can about the density matrix. But if you've already determined that, then measuring the entanglement entropy is not independent. Okay, so people criticize whether you're really measuring the entanglement entropy or whether effectively you have managed to measure what you can measure of the density matrix. But certainly it's something that people talk about trying to, not just as a computable, but something that you can measure.
So what's the issue that these two measurements do not commute?
No, that they're just not independent of each other. So that if you're making measurements which effectively determine the density matrix of the system, then you've already got all the information you can get out of the system. And so you're not really measuring the entanglement entropy specifically, you're just measuring the density matrix. So that's a criticism my condensed matter colleagues make of these measurements. They often involve maybe 4 atoms. So, it's essentially 4 qubits they're trying to measure. So are you really measuring the entanglement entropy or are you really just determining the whole state of the system? Okay, is this measurement something which would generalize to a large number of atoms? And the answer is probably no. Okay. Now, so this was a sort of review very much from the perspective of a condensed matter physicist. Now, in recent years, people have been interested in using entanglement entropy in quantum field theory, in which there is really an important logical difference. So once again, we are interested in dividing our background for our quantum field theory into 2 parts. And again, on very general grounds, we expect that the entanglement entropy, the leading contribution, at least in the ground states of our quantum field theory, the low energy states of our quantum field theory, has a divergence which scales with the area of the boundary of the entangling region. There'll be subleading divergences, they may be logarithmic divergences. Again, I'm not at this point assuming that I have a quantum critical theory or a gap theory, I'm just asking for the generic behavior. Okay, but now the important conceptual difference is the following. So this is again dimensionless, and so these coefficients, these C's are all dimensionless, and so the powers of L, which characterize the scale of the region, must be balanced by an appropriate dimension full parameter, and the dimension full parameter here is the ultraviolet cutoff of the theory. Okay, so now we don't think about having an underlying discrete system. We really had to introduce an ultraviolet cutoff. And so for those of you in the room who've been working on entanglement entropy for some years, you're sort of used to this, that you're working with a quantity which is cutoff dependent. But if you showed this to somebody who works in quantum field theory and who hasn't been working with entanglement entropy, they would say this is a really strange thing to do, because you don't usually work with cutoff dependent quantities. Yeah? So I'll come back to that in a moment. Now I should say, another issue with, so why do QCD physicists not work with entanglement entropy? Well, actually they do, and I'll come to that a little bit later. Some of the lattice theorists do. But the point is that entanglement entropy is intrinsically a very hard quantity to calculate. So if we think about what we were calculating, we had to know the density matrix of the system, and we also had to calculate the logarithm of the density matrix, which is not a nice calculation to do in linear algebra. Now, in practice, how you calculate it is by cheating slightly. So you realize that you can write trace of rho log rho as the differential of trace rho to the n with respect n and then setting n equals 1. Okay, so this is formally equivalent to the expression I had before. Okay, and calculating powers of the density matrix is at least easier than calculating logarithms. But it's still very hard to do outside free theories or integrable theories. So it's not an accident that the state of the art in entanglement entropy for analytic calculations is free massive theories. And actually, it's only in the last 10 years that people went to free massive theories in 3 or 4 space-time dimensions. A lot of the work before that was in 2 dimensions and lower. So these things here, these things in brackets, are called Renyi entropies. They're called SAN. And these themselves are not believed to be observables. Now, you could also complain here that whilst I did a formal manipulation, there was an implicit assumption in my formal manipulation, which is that this has an analytic limit as n goes to 1. And that is something which is inherently something rather unreasonable, right? Because this thing here is clearly calculated well for integer n. You can take integer powers of the density matrix. But there's no reason a priori that this should then be analytic, viewed as a function of n, and taking the limit n goes to 1. And it happens in practice that it usually is the case that it's analytic, but there are indeed examples where it's not analytic. So that's a conceptual issue. So the reliance of this trick on this trick is not satisfactory because there is no a priori reason to believe that this would be analytic as n goes to 1. You have to test it case by case. There's also an obvious problem with my definition of entanglement entropy in gauge theories, which is that the Hilbert space does not factorize. I assumed a factorization which simply does not exist in gauge theories. And again, that's a long-standing issue which people have explored, and to some extent they tend to solve by sort of cheating, by evading. So if you work with gauge theories in low dimensions, you can actually just use Poincare duality to write them in terms of scalars and so on, and you evade the issue that way. But it's something which is really not very well understood. Now, the other conceptual issue, which is the focus of today's discussion, is the thing that I've noticed here, which is that the quantity is naively UV divergent. And in fact, it's sort of worse than that because, well, worse. It's clearly dependent on the scheme that you use. So if you look at the calculations that people do, they will typically use heat kernel type techniques. And again, if you're a quantum field theorist, you might say at this point, well, so why did you not use dimensional regularization or zeta function techniques? I mean, dimensional regularization in particular is usually how we do regularization in quantum field theory. And actually, if you use these techniques, you don't get power law divergences. So why did the condensed matter physicists not use these techniques? Well, for them, the cutoff is a real physical cutoff in their system. They will actually want to interpret these terms so that epsilon will really be a lattice spacing in their system. They want to actually, attach a physical interpretation to those terms. And so for them, it was natural to keep those. But if you're interested in interpreting this in a quantum field theory, it's very unsatisfactory that you seem to be getting a different answer, that these terms are not universal. You get a different answer depending on which regularization scheme you use. And actually, I would highlight the fact that having been, raised by Stephen Hawking, the zeta function techniques are actually very well adapted to calculating this quantity. So there's a lot of literature from zeta functions that one could use to calculate this quantity. It's quite natural to do so, but you would not access power law divergences that way. You would access only the log terms. Now, the log terms do show up in all renormalization, regularization schemes, and that's why sometimes they're called universal. And in some sense, the fact that they were more universal, if we flip back to here, this was already manifest in the fact that they came with the factor A, which is the coefficient of the Weyl anomaly of the theory. So it's something where you say, okay, well, this looks like this comes from anomalous transformations. It seems to have some physical some physical background. This term is something that we would expect to see, and indeed you do see it in all regularization schemes. But it's still, as I said, very unsatisfactory that what we get is something which is regulator dependent. Okay, so now, having noted this issue, I'll come back to it later. Now I'm going to switch to holography. So I'm in a slightly more general context than I was the other day. So I'm going to be talking about a quantum field theory in d dimensions and gravity in d+1 dimensions. And for me, a special case of this is when the quantum field theory is a conformal field theory and the gravity is anti-de Sitter gravity in d+1. And I remind you that what we discussed the other day, we said that we didn't have to be in the case that we have conformal symmetry. We can realize explicit and spontaneously broken symmetry. We also have realizations of phenomena such as confinement and so on. Now, in holography, the other thing that we mentioned, although I didn't illustrate it in such a diagram, is that the ultraviolet physics of the quantum field theory is captured by the near boundary behavior. So in the picture on the left, the boundary of the space-time is meant to be on the right. The interior of the space-time is on the left here. So as we go out here, we're going towards the boundary of the space-time. So the infrared physics is captured by the deep interior. And so short distance scales in the quantum field theory are probed by things that are happening in the boundary. Long distance scales in the quantum field theory extend deeper into the bulk. Now, the other thing we discussed on Monday was that the natural holographic computables were the partition function and correlation functions of gauge invariant observers, gauge invariant operators. Okay. Now, the partition function played a role in the construction of the entanglement entropy. So from that perspective alone, it would be natural to think that the entanglement entropy would be something that you could calculate holographically. And indeed, not with that reasoning, but 10 years ago or 11 years ago, Ryu and Takiyanagi proposed that there was a simple prescription for calculating entanglement entropy whenever you had a holographic description of a quantum field theory. So again, we're interested in entanglement entropy where we have a region A and a region B, and the boundary of A is dA. And so we want the entanglement entropy in a given state of the quantum field theory associated with A. So apologies, my figures keep switching, they keep rotating by 90 degrees. So now the boundary of the space-time is up at the top, and going into the interior goes down the board into here. So their prescription was that what you have to do to calculate the entanglement entropy is to find a surface which is homologous to A, which extends into the bulk. So it's like, taking a piece of rubber and putting a marble or something on it and letting it sort of, shrink down into the bulk. So the shaded surface here is the surface that goes into the bulk. And it should be codimension 2. So here I'm working with constant time. So if I was in 4-dimensional anti-de Sitter, codimension 2 means I have a 2-dimensional surface. And that's what indeed is happening here. And this should be homologous to A. So if I should be able to continuously shrink my surface sigma and get to A. So I find this minimal surface. By the way, there was a conference in the Fields Institute with mathematicians a month ago, and we spent the entire conference arguing whether this should be called minimal or extremal with mathematicians, and with no definitive conclusion. A more general case with it, yeah. So yeah, we had, even in the static case to some extent, but we had a long dispute about this. But okay, let's stick with the physicist's definition of what is minimal here. So we will extremize the area and take the minimum area. Now, to get the entanglement entropy, we take this area of this surface, we call it curly A, and then we measure that in units of the Newton constant, so 4g, the Newton constant. And so as I said below, if we have a 3-dimensional quantum field theory, we've got a 4-dimensional gravity theory and a 2-dimensional minimal surface. And for the purpose of this talk, I'm actually really suppressing time. And so, you see the picture I have here. So I have a shaded region A, which is 2-dimensional. And then the surface, which is homologous, is the purple shaded region, sigma. Okay, so now let's see what their evidence was in 2006 that this was correct. So this, in some sense, almost came from nowhere, right? I'll derive it a little bit later, but it almost came from nowhere. Okay, so let's see whether this is going to work. So we know that there's a correspondence between anti-de Sitter and conformal field theories. So let's just check that this prescription will actually reproduce the known behavior of entanglement entropy in a conformal field theory. So just as I did the other day, it's useful to write the anti-de Sitter metric in so-called Poincare coordinates. And we know we're going to have to introduce a regulator. And the natural regulator is just to cut off the boundary at, instead of taking it to rho equals 0, to set rho equals epsilon, where epsilon is much less than 1. And if you just go through the calculation and you take a surface of constant time, homologous to a region A, you can actually just show rather straightforwardly, in fact it follows directly from the powers of rho that sit in the metric, that indeed the area of this surface goes as the area of the boundary of dA scaled in units of the cutoff, and then indeed there is a logarithmic term which shows up in the right dimensions. So this was, their primary evidence that this was the right prescription for entanglement entropy, holographic entanglement entropy. It was that you got the expected behavior that I showed you before for a conformal field theory. And I said that there's a regulator dependence. In fact, that would come into holography as well. So people usually use a direct radial cutoff in holography. But if you wish to, you can use dimensional regularization. So our former student, Adam Bazowski, has recently developed dimensional regularization for in the context of holography. And as indeed expected, if you use dimensional regularization, you don't get the power laws, but you still get the log terms there. Okay. But again, in holography, people almost always use a direct radial cutoff. Now, why is the entanglement entropy computed by minimal surfaces? So this was a puzzle for a while, and there were various arguments in various cases. But really, the derivation came from Levkovitz, Modesena. Sorry, I think I should have a citation to them there. So it really comes using the replica trick. Now, I might be a little bit cautious about using the replica trick. So the replica trick was this trick of taking the n goes to 1 limit of the Rényi entropies. Okay, and my concern there was that the Rényi entropies, it was far from obvious that they were analytic in n as n approached 1. Okay, but okay, let's assume, or let's for now proceed with this trick. Okay, so the formula I had, so let me go back. Apologies, I don't want to flip too much, but let me go here. So this formula here, so trace of rho to the n is the partition function, we're going to call it Zn, and trace of rho itself is just going to be the ordinary partition function. Okay, so I can just rewrite this Rényi entropy in this form. So it's the log of the partition function Zn's minus n copies of the partition function, the usual partition function. So this is just a rewriting of the formula that I had before. So the thing that's peculiar in here is the Zn. So the Zn is the partition function on a replica space, so it's our way of computing essentially the trace rho to the n. We take n copies of the original space and we join them together. Okay? So let's think about what we're doing. So this is, again, an illustration of a three-dimensional quantum field theory. The x0 direction is the time direction. And we're considering a region which is just in space. So this is our shaded region. This is just a region in space. Okay? And so what we asked to do is to take copies. We will take an integer number of copies, and we will join them together. And what we will do is we will take, there's clearly a circle that bounds the entangling region. So this is the entangling region. This is a circle that bounds it. We normalize the coordinates so that in the original space it has period 2 pi. There's no conical singularity here, so we can always choose an adapted coordinate system such that tau has period 2 pi. And then in the replica space, we choose tau to have periodicity 2 pi n. Now I should comment here actually, following a remark the other day, it's actually always important to remember that tau is not the time. And this is, I think, very clear from my picture here. So the time is going in the vertical direction, okay? But the tau, which is the circle which bounds my boundary of an entangling region, that's not the time. It's called tau because in some sense it plays a role of imaginary time in the, it's got a periodicity, but it's not actually the time. Okay, so we glue n copies together. Now, to visualize gluing these n copies is pretty difficult. So I kind of take a slice through the vertical plane here. So the plane in which I've shown the tau circle, I take a slice through that, and then I take 3 copies and join it together. So what happens is, as you take these copies, so here's again a sort of slice, an x0, x1 slice. So we take our 3 copies, that's the first one, that's the second one, that's the third one. I should say the vertical lines, you know, are in a sense, artifacts of the drawing. They shouldn't be taken seriously. So you're just taking the 3 copies and you're joining them together. But what this image is meant to show to you is that when you do this joining, you've clearly got a conical singularity about the origin of your tau coordinate. Okay, and you would have expected that, right? Because you chose your tau coordinate to have periodicity 2 pi in the original space so that it didn't have a conical singularity. If you now take multiple copies of it, you're actually going to get a conical singularity. And so the point you see here, that's where the conical singularity is. Okay, so your replica space will have a conical singularity at the location of the boundary of the entangling region. Okay. Now, okay, let's come to the Lefkowitz-Moldassana derivation. So, yeah.
At this point about tau not being time, well, it's clear
Yeah.
that there are different coordinates and that's important, but is it the case that you're necessarily in Euclidean signature, so then really time could be in any direction, or is that?
So I have, I mean, I'm not necessarily in Euclidean signature actually for this approach. I mean, I can be in Euclidean signature, but you mean if there is a physical temperature of the system, i.e. x0 is periodic, yeah, this will be a different periodicity to the tau periodicity, yeah.
So I meant being in Euclidean signature so that your path integral computation gives you the vacuum. But just that I suppose it is needed.
The path integral, it gives you the vacuum. Well, it can also give you non-trivial state, right?
Oh, if you insert it.
Yes. Yeah.
Okay.
Yeah.
But I mean, use the path integral computation to select a specific state. Normally, are working in Euclidean signature.
That's right. That's right. That's right. But still, tau is different from the Euclidean time. Yeah. So if you're working at finite temperature, there will be 2 periodicities in the game. So there will be the first one will be the periodicity of your real imaginary time, and the second will be the periodicity of that. Okay. Okay. Now, so we want to calculate the entanglement entropy by computing the partition function on this replica space, which has a conical singularity. But remember, the thing I told you was that the partition function is something that ADS-CFT is really good at calculating. So in the relation for the defining relation for holography was that the partition function was the on-shell value of the action. Okay, so that was the defining relation I wrote down for you the other day. Log of z is minus the on-shell Euclidean action. And so in particular, this is we're just doing, Einstein gravity with a cosmological constant. There might be some matter there. That's what the dots are. Now I've kept track of my Newton constant, so it's 1 over 16 pi times the Newton constant as a prefactor. The replica space has a conical singularity. So the curvature of the replica space, so remember we glued together n copies of the original space, but we've got a conical singularity. So whilst locally throughout most of the space, the curvature of the replica space, the scalar, Ricci scalar, is the same as the curvature of the original space, at conical singularity, you get extra contributions. And in fact, these contributions were calculated in many places. In particular, there's a nice paper by Solodyukin from 2008, where he calculates not just the Ricci scalar, but many other scalar invariants, Riemann squared and so on, for spaces that have conical singularities. So when we use the replica formula, the on-shell action, the contributions to the on-shell action between the replica space and the n copies of the original space, they're going to cancel almost everywhere. But at the conical singularity, the replica space will have contributions to the curvature and hence the action, which the original space didn't have. And so when you go through that calculation, all of the terms cancel, apart from the contribution from the conical singularity, which was on this codimension 2 surface. And actually, if you just plug in this form for it, you'll figure out that the contribution that survives is just the area of the original surface. So this is the derivation of the entanglement entropy using the replica trick. I should say, actually, Modesena and Lefkowitz and Modesena, they do this in pictures, actually. This is done in formula here, and it was done in the paper with William Woodhead in formula, because this really emphasizes that you can actually do this in higher derivative gravity theories. So your favorite, Gauss-Bonnet, with matter coupled to curvature, you just follow exactly the same derivation, and all you need is the formulae for the curvature invariance, the conical singularity contributions to the curvature invariance. So if you've got Gauss-Bonnet gravity, for example, you need, of course, you've got all your curvature squared terms. So you need, to take the formulas from Solodukin for the contributions coming from the conical singularity, and then you can go ahead and you can calculate the analog of this formula. So in higher derivative gravity, it's not, the entanglement entropy is not just the area of the minimal surface. You get a different functional, but you can get this from the same approach, which we do actually. I mean, of course, Lefkowitz and Modesena themselves had a different route to arguing the functional for higher derivative gravity, but you can do it, in a sense, in a cleaner way by this approach. Okay, now, what do we want to use the holographic entanglement entropy for? So as I said, so now we're using, we've got a holographic description of a quantum field theory. The condensed matter physicists were really interested in entanglement entropy in this kind of discrete system. So what was it going to be? What do we want to use it for? Well, the whole point of this is that we said that entanglement entropy was very hard to calculate in theories which were not free or integrable. We said that it was really very difficult to think about how to calculate entanglement entropy in a gauge theory, because you don't seem to have a natural partition of the Hilbert space. There seems to be an issue with how you implement gauge invariance in direct perturbative computation. But anything you calculate in holography is implicitly gauge invariant. And so what we have is a simple prescription for getting the entanglement entropy. You just go and get this surface, and you will be able to compute the entanglement entropy in a large range of large n, strongly coupled gauge theories. In particular, as I said, we have gauge theories which exhibit confinement. We have holographic descriptions of things which are strongly coupled superfluids. So this is why the game in town for the last 10 years or so has been to go and explore entanglement entropy in these cases. And as we said, the small entangling regions probe the ultraviolet physics. The larger regions, by taking your region to be larger, you're clearly, your surface will go deeper into the bulk, and so it's probing infrared physics. And so entanglement entropy is something which is useful for probing infrared behavior of the theory, whether it's confining and so on. And that's something which, again, about 10 years ago, people really started to think about. Well, just to repeat a remark from the other day, my former colleague Robert Digraph used to describe the string theory world as a hamster's wheel of things which go round in fashions. And the thing that's at the top of the wheel when you're a student is the thing that's at the bottom of the wheel a few years later. And the thing that you thought you never ever would need to know comes back and gets you. Like matrix models was something I never thought I would ever need to know, because I thought they went out of fashion in the sort of 90s and then they came back again. For those who've been around long enough, you could make the very reasonable comment that actually entanglement entropy doesn't do more than Wilson loops do. So Wilson loops are actually calculated holographically via two-dimensional minimal surfaces. So if you're calculating in four-dimensional gravity, the minimal surface, the entanglement entropy calculation is almost identical to the Wilson loop calculation. So Wilson loops, we have to specify representations and things like this, what kind of Wilson loop, but we're basically doing the same calculation. If we go into higher dimensions, say 5 bulk dimensions, the entanglement entropy is using a 3-dimensional minimal surface. The Wilson loop uses a 2-dimensional minimal surface. But nonetheless, they're basically accessing the same thing here in the sense that you're in both cases sending a surface down into the bulk. So there was a sort of a game of people repeating their Wilson loop papers to do entanglement entropy, right? Whereas 15 years ago, people would have done a Wilson loop calculation. They now do an entanglement entropy calculation instead. Okay, now let me move to entanglement entropy and CFTs. So let's go back again to these universal terms for the ground state of a CFT. So we said that we always got these logarithmic terms. We might get power law divergences, but that depended on our regularization scheme. But for all regularization schemes, for CFTs in even dimensions, we get these logarithmic terms. And in particular, in 2 dimensions, somewhat confusingly, the A anomaly is actually called C. This was actually because when people first labeled the anomalies in 4 dimensions, they got the labels the wrong way around, actually. They labeled one of the anomalies as C, which is really not the analog of the 2-dimensional anomaly, so the labeling is inconsistent. But okay, in 2 dimensions, this coefficient is basically the C, which is the coefficient of the anomaly. And so the very famous homological C theorem proved 30 years ago says that the C function is something, the C quantity is something which monotonically decreases along a renormalization group flow from the ultraviolet to the infrared. It's something that's stationary at fixed points. It's something that is positive. It's something that measures the number of degrees of freedom of the theory. So it's a long-standing puzzle to generalize the Zamolodchikov C theorem to even dimensions. There's a lot of progress with the A theorem in 4 dimensions. 6 dimensions, I think, is still tricky. It's very hard to prove things. But, an analogous story basically works in 4 dimensions. This is the Komogodsky and Schwimmer sort of almost proof of the A theorem. But there's a long-standing question, which is that if you use the coefficient of the trace anomaly to measure the number of degrees of the freedom, what do you do in odd space-time dimensions? Because on dimension-full grounds, there's no trace anomaly. This automatically vanishes. So if you're in a supersymmetric theory, you can use the relationship between the stress tensor and the so-called R current of the theory and look at the correlators of the R current and kind of get a candidate. But if you don't have supersymmetry, so that's in Trilogator and Weck's work, but if you don't have supersymmetry, you should still have some natural measure of the degrees of freedom. So what's the quantity which is going to measure the degrees of freedom? So it seems like a little bit of a side to this talk, but it turns out to be something which is intimately related to entanglement entropy. So it's been proposed in particular by what was then the Princeton group of Jafaris, Klebanov, Pufu, and Safdie, that the quantity which counts the number of degrees of freedom in a 3-dimensional conformal field theory, and there are analogous conjectures in other odd dimensions, 5, 7, and so on, is the quantity you get by computing the partition function on a 3-sphere. Okay, so we calculate the F quantity in terms of the partition function on the 3-sphere. And let's note again that the fact that this is expressed in terms of a partition function means that this is something which is going to be beautifully computable in holography, right? So we just need to put the field theory on the curved background, take the gravity which captures this, calculate its on-shell action, and that will give us the F quantity. So their conjecture was that the F quantity is something which is, again, stationary at the fixed point, positive in a unitary conformal field theory. I should have said before, of course, Zamolodchikov requires unitarity as well. And it should decrease along an RG flow so that the ultraviolet F is always greater than the infrared F, and the equality holds only if you have exactly marginal deformations. So this is the F conjecture. Now, what has this got to do with entanglement? Well, the sphere partition function and the entanglement entropy for a disk entangling region in flat space. So we've got a 3-dimensional quantum field theory, 2-dimensional spatial sections. So we take a disk region. These are related to each other, and they're related by the so-called Cassini-Hürter-Myers conformal map, which I will tell you about. So let's start with the geometry in flat space. So this is just time, and this is just flat space and polar coordinates. So it's straightforward that if you just take the region of R less than capital R, you've got a disk of radius capital R. You do a coordinate transformation, from T and R, the original time and R radial coordinates, to new coordinates, theta and tau. And this just, you can just plug this in, and you get something which is conformal to de Sitter space. So the thing in brackets here is just de Sitter space, and there's a conformal factor which you don't need to know. So we're doing conformal field theory, so any conformal factors will not play, well, they may give us conformal anomalies, but basically the theory is invariant under conformal transformations. And so if we look at the range of this map, the de Sitter is associated with the disk region in the original coordinates. Okay, so the map takes you from the interior of the disk in these coordinates to the whole of de Sitter space. Now, if you follow this conformal map, so we started with just the trivial vacuum in the original space, but now the information about the radius of the disk is captured by the fact that the state we get in de Sitter is thermal with a periodicity proportional to the radius of the original disk. And so the entanglement entropy for the original disk is just mapped to thermodynamic entropy associated with the thermal state, and that in turn is just related to the partition function. So when you have a compact space like de Sitter, so it's okay, let me step back. You analytically continue de Sitter, you get a 3-sphere. This is a compact space, so the entropy is just related to the partition function. So this, of course, is well known. It goes back to Gibbons and Hawking's discussion of the entropy of de Sitter space. Okay, so the entropy of de Sitter is related to the partition function of de Sitter, but again, de Sitter, when you analytically continue the time, that just becomes a 3-sphere, and so the disk entanglement entropy just is precisely proportional to the partition function on the 3-sphere. So this is the statement of the Cassini-Herter-Myers relationship. Now, we have a conjecture that the partition function on the S3, the F quantity as it's called, is the quantity that counts the degrees of freedom. But this means if it's equivalent to the disk entanglement entropy, the disk entanglement entropy should also be counting the number of degrees of freedom in the quantum field theory. Okay. But there's a puzzle, and it's a puzzle which I think should have been clarified much earlier in the literature, which is that unlike the A anomaly coefficients which show up in even dimensions, both the F, the S3 partition function, and the entanglement entropy are ultraviolet divergent. So I already told you before that the entanglement entropy seems to depend on the regulator I use. Whenever you calculate a partition function in quantum field theory, you've got to do some form of regularization, renormalization. Now, implicitly in the literature, people have used a method of renormalization. And they have used a different method of renormalization depending how they calculate it. So people who calculated F with quantum field theory methods usually use dimensional regularization methods because that's what you usually do in quantum field theory. When they calculated it holographically, they used implicitly holographic renormalization, which we touched on the other day. What they never discussed was scheme dependence. They never discussed whether their answer would depend on the scheme that they actually used. And so this is where renormalization comes in. So this is one of the main contents of the paper with William Woodhead from last year. So the first claim is that the finite part of F is indeed renormalization scheme independent, i.e. you can't add any finite counterterms. So you will get the same answer regardless of whether you calculate it in dimensional renormalization, zeta function, direct cutoffs, whatever you do, direct counterterms. It's renormalization scheme independent. It's crucial that we're in odd dimensions for this to be true. And the second statement is, we said that the F quantity, the partition function on the 3-sphere is related to an entanglement entropy on a disk. For this relationship to make sense, you must be able to define a renormalized entanglement entropy, and indeed you can, and the renormalization is again inherited from the favorite method, whatever method you use to renormalize the F quantity. Okay, so now the first part I could prove for you in quantum field theory by analogous techniques to those used by Komagotsi and Seiberg and Schwimmer and Tyson and Gomis and others. I'm not going to do that here because it's a bit of an excursion, it will take too long. So I'm just going to give you a cheaper argument, the easier argument, which is in holography. Okay, so if you calculate F using holography, what do? So you take anti-de Sitter with an S3 boundary, and you calculate the on-shell action. That's how you calculate it. And you need to use the renormalized on-shell action, which was calculated by Sebastian de Haro, Sergei Solodyukhin, Kostas Skenderis in 2000. It's a very well-known paper. So we take the anti-de Sitter action. That's just the cosmological constant there. I've just pinned the radius of anti-de Sitter to a unit radius. So that's just the cosmological constant. So that's the Einstein term. I should say here I've also missed a term, actually. I should have the Gibbons-Hawking term here, so the term missing in the expression. But the important term is these terms. So these are the covariant boundary counterterms that you add to renormalize the action for anti-de Sitter. In maths terms, you mean you're renormalizing the volume of the space. Okay. And just as I said before, in our toy example involving a scalar field, the counterterms need to be covariant. They need to be expressed in terms of quantities which are intrinsic to the boundary. So they're expressed here in terms of the boundary metric, and the curvature, curly r, is a curvature of the boundary metric. They're expressible in terms of the boundary metric and its scalar curvature invariance. Now, there are no possible finite covariant counterterms. So these two terms, they cancel divergences. They give you finite contributions as well, but they're there to cancel divergences. Okay. You can't just add terms which would change the finite answer with arbitrary coefficients. And the cheap way to see this is because the scalar curvature invariants are even dimensional. And if you just do a dimensional analysis, you will see that actually they would never contribute at order epsilon to the 0, so epsilon is the cutoff. They always contribute at odd powers of epsilon. They can never contribute to finite counterterms. Okay, so that's the cheap argument. And actually for Alberto, it is spelt out in some detail in that paper. Okay, so if you calculate the renormalized on-shell action for ADS4 with S3 slicing, I should say the way I've normalized it, the Newton constant here is dimensionless. Might be a little unconventional, but it's dimensionless. The on-shell action is minus pi over 2g, so the F quantity is pi over 2g. In other words, the inverse Newton constant counts the number of degrees of freedom. Right? So this is manifestly positive because g is positive. It counts the numbers of degrees of freedom. And in fact, I should say that this calculation, this is in itself not new, because people have been trying to match the F quantity calculated with localization techniques, matrix model techniques such as Marcus Marinho and co. had already calculated this holographically. So, you know, they'd done this in the context of ABJM and so on. They'd actually found this value using, in fact, you know, the bulk of the calculation is really done by these guys by giving us the counterterms. Yeah. So this was unknown. Now, let's go back to the entanglement entropy. So we recall that in practice, when we calculate the entanglement entropy, we do so by using these Renyi entropies and this replica trick. So we did it by this calculating the partition function on a replica space and taking, you know, subtracting n copies of the original space, taking the limit that n goes to 1. So in this expression, it's actually clear that you can immediately go to a renormalized entanglement entropy just by working with renormalized partition functions. You can use whatever renormalization scheme you like, zeta function or whatever. You can use any renormalization scheme. And implicitly, if you understand the renormalization scheme of your action, your partition function, you will understand the scheme dependence of your entanglement entropy. So there are cases, you know, for quantum field theories in even dimensions, you definitely have, or conformal field theories in even dimension, you definitely have finite counterterms possible. You know, my argument precisely goes wrong in this case, right? There are definitely finite counterterms possible, and you will have scheme dependence, but you will understand how it's inherited directly from the finite counterterms of the partition function. And why is this valid? So actually, you know, it's valid because you might worry about these replica anomalies. So in particular, you may worry that this is not analytic as n goes to 1. But actually, the divergences and the counterterms are really about local behavior. And replica problems with the analyticity as n goes to 1, are really associated with global effects. Okay, So actually, you really only need to construct the replica locally to calculate the entanglement entropy counterterms. So any possible concerns one has about replica trick it's really a non-issue here because it just doesn't come into play. Okay. Now again, we could have this discussion from the quantum field theory. There is a paper which William and I have been writing for a long time, but William has now gone to work for IBM, so it needs to be finished, on doing this in quantum field theory, so calculating this in quantum field theory with different cases of perturbative quantum field theory. But actually it can be beautifully illustrated in the holographic calculation where we have a very natural way of doing the cutoff, okay, and doing the renormalization. So here's our entangling surface. So what do? We're trying to calculate the area of the surface. Now, we're going to renormalize the area with appropriate counterterms. So we're going to cut it off. Again, as usual, the boundary is at rho equals 0. We cut it off at rho equals epsilon. And we renormalize using appropriately covariant counterterms. And in fact, as I said, entanglement entropy was preceded by minimal surfaces. So people had already renormalized minimal surfaces in the literature. So this is not the famous, well, it's a well-known paper, but it's not the famous Henningsen-Scanleris paper. This is the Wilson-Loop paper. They already did it there. Robin Graham, the mathematician, worked with Ed Witten to discuss renormalized minimal surfaces. And the math community now calls this area renormalization. They standardly renormalize the area of minimal surfaces in hyperbolic spaces using this method, right? They don't tend to refer to our community even when they use our results, but the math community very certainly do this. And I should say it actually plays a role in higher dimensional generalizations of the Wilmore conjecture. The Wilmore conjecture was a statement about embeddings of surfaces, two-dimensional surfaces in 3 dimensions, which is proved by mathematicians recently. There are higher dimensional versions of this conjecture which rely on renormalized area, actually, and well, I'm working actually with Robin Graham on. David Gross, you may be surprised to see his name here because he hasn't been so active in string theory in recent years, but he also renormalized the areas of minimal surfaces in the context of Wilson loops. So what I'm saying is in the context of almost every other calculation in holography, people did not want to work with regulated dependent quantities. They'd renormalized. Okay? And it's really entanglement entropy that people had been happy to work with regulated quantity because the condensed matter physicists did. But the condensed matter physicists work with the regulated quantity because they really have a lattice cutoff in their system. It's qualitatively different. Okay, so what are we going to do? So first I'm going to do it brute force, and then I'm going to do it a cleverer way. My poor student did it brute force, and it took him 3 months, and I did it the clever way and took a day, right? Which is a lesson in pain for students. I didn't realize you could do it in a day, but I would have still made him do it the other way just to check. Okay, so the Ryu-Takenagi functional is just this area functional. Okay, so what we need to do is we take the equations of motion for the minimal surface, we expand the area asymptotically near the conformal boundary, we regulate the divergences. So this is complete analog of the toy scalar field calculation that I was doing before, but the analysis is a bit more complicated because actually the minimal surface equations are a bit more complicated, but it's exactly analogous. And now what we do is we need to invert the divergences by writing them in terms of covariant counterterms on the boundary. And the new feature is, or the new issue is to decide what you mean by covariance. So covariance here means the following. So I think perhaps best illustrated by the picture on the next slide. So we're looking at counterterms which are on this line. They're living on the boundary of our entangling region, and our holographic surface goes into the deep of the space-time. So we've got some gravity description in one more dimension. So our surface goes into the space-time, but it ends on the same boundary. Now, our counterterms should be intrinsic to this green surface. That means that they can depend on the intrinsic curvature of our boundary dA. So in the case I've shown, it's one-dimensional. So the intrinsic curvature is trivial here. There's no intrinsic curvature. If it was higher dimension, of course, there'd be intrinsic curvature too. But there is extrinsic curvature, or second fundamental form. Extrinsic curvature is about how this line is embedded into this surface. Okay, so the extrinsic curvature is what I call kappa here, the second fundamental form. Now, there's an important restriction. So I said at the beginning that in the case that we had a the state of the quantum field theory was pure, the entanglement entropy of A matches the entanglement entropy of B. This is called complementarity. And for that to be respected by the renormalized entanglement entropy, you can only have terms which are even in the extrinsic curvature. Because A viewed as embedded into B, the extrinsic curvature points outwards. Well, you choose a convention, but it points outwards. B embedded into A, the extrinsic curvature is in the opposite direction. Okay? And so if they're going to have the same renormalized entanglement entropy, you need to have only terms which are even in the extrinsic curvature. So we've got two rules. Our counter terms can depend on intrinsic and extrinsic curvature, but it can only be even powers of the extrinsic curvature. Okay, so let's go and do this for 4 dimensions, ADS4. So this is really pure ADS4 and a 2-dimensional entangling surface. So this is the Ryutakyanagi functional. This is just the area function of the minimal surface, which would be divergent. And then the counter terms, we've got 2 of them. So one is just the length of the curve that bounds the surface. And we've got a second possible finite counter term. So here we are allowed something which is a finite counter term, apparently. But this depends on the extrinsic curvature as a bounding curve. So it depends on the extrinsic curvature of this curve embedded into the surface. But you see, this breaks my rule because this is an odd power of the extrinsic curvature. So I'm not allowed that counter term. It would not respect complementarity. And so I have to set that to 0. I mean, I could argue it the other way around. I could say, well, it's just never there because it just doesn't respect my rule of complementarity. And so really, it's just this is the only counter term that's actually needed. I should say, in case you think this is sort of too trivial, as soon as you go to more general backgrounds, backgrounds with scalar fields as well, the counter terms become increasingly non-trivial, right? There are more counter terms than this. Okay, so now let's calculate the entangling region for a disk of radius r. If we actually just calculate it, you just plug it into this formulae, then you see that actually the radius r drops out, and you get that the renormalized entanglement entropy is just minus pi over 2g. And that's exactly what we expected, because the F quantity by the Cassini-Herty-Myers map was mapped to the entanglement entropy of the disk region. There was a minus sign in the map, actually. And so the positivity of F indeed required the negativity of the renormalized entanglement entropy. You could say that, actually, if you wanted to define a physical quantity, perhaps the physical quantity would be precisely the minus of this, because it's counting the number of degrees of freedom. So minus the renormalized entanglement entropy counts the number of degrees of freedom. Okay, so the renormalized entanglement entropy, so this was a brute force calculation. I didn't show you the details, but this was, really just a brute force calculation that I would just take the equations of motion. I would do the analog of what I was doing the other day with my field expansions as powers of epsilon, powers of r, plug it in and just do it brute force. But there's a cleverer way of doing it, which is to use the replica trick on the renormalized on-shell action. So, given my household already calculated, 17 years ago in gory detail, and it took them about 2 years, or year and a half, all the counter terms of the renormalized action, in all dimensions, so ADS4, ADS5, and ADS6, I can just use the replica trick on what they did. So, for example, the asymptotically locally ADS4 spacetime, this is the same counter terms as I wrote down before. I should say that here I've put the Gibbons-Hawking term back in again. This was the curvature of the boundary metric. Okay, and so following exactly the same logic as I did for the derivation of Ryutakyanagi, again, when I use the replica trick, the only difference between the replica space and the n copies of the original space is the contributions which really come from the conical singularity in the replica space. So the curvature of the replica space, boundary of that, gets an extra contribution which is localized on the boundary of the entangling surface. And again, I use the formulae that Solid Yukon has helpfully written down. And so if I just plug that into the replica trick, I just plug it in, then again, I come up with exactly the same counter term that I had before. So this is very nice, it's very elegant, And the point is that now, I did you the most trivial example, but as you start going up in dimension, the counter terms, both for the action and the entanglement entropy, start to become quite complicated quite quickly. And so we can use this trick, and we can actually just work out the counter terms for ADS Einstein gravity in any dimension. So any case where people already did the holographic renormalization of the action, I can get the counter terms for the entanglement entropy within a sort of a two-line calculation. So in particular, if we go up to Einstein gravity in any dimension, you always get a term which is related to the area of the bounding surface. There's always that counter term. Sorry, the area of the boundary of the entangling surface. But then there will be, as you go up in dimension, you get a term which indeed depends on the extrinsic curvature squared. So that respects our complementarity principle because it's a square, and so on and so forth. And so you can just go to the paper. If you want to compute entanglement entropy in ADS 5, ADS 7, whatever it is, you can just go to the paper and get the counter terms from us. And we can do it with theories with matter, and you can do it with theories such as Gauss-Bonnet. Actually, I should say that the issue with Gauss-Bonnet is that people have struggled to find the counter terms for the action because it's so complicated. So in some sense, this is a cross-check. You do the explicit calculation of the counter terms for the entanglement entropy, and you cross-check it against using the replica trick to actually check the counter terms that people have had. And as I said, you also directly inherit the renormalization scheme for the entanglement entropy. Where there are finite counter terms, you will directly inherit the choice that you made for the action. So that's also nice. Okay, so now let's turn to what happens to the F quantity. So we've matched the F. We've said we've done the calculation now, and we said that the F quantity on the 3-sphere is indeed equivalent to the entanglement entropy of the disk in the holographic example I did for you. But the conjecture about F is something stronger. The conjecture of F is not just that it's positive and stationary at a fixed point, it's that it actually decreases along a renormalization group flow. Okay. So if you make a relevant deformation of the 3D conformal field theory, the conjecture is that the F quantity should decrease. And in particular, if you follow the same logic as Zamolodchikov, Zamolodchikov worked perturbatively in this coupling. So lambda is the coupling of the deformation that you make. The first, if you work to order lambda cubed, this the term at lambda squared should be strictly negative. It should decrease. And according to the CHM map, the entanglement entropy should increase. It should go in the opposite direction. Okay, now there's a lot of evidence in both perturbative and holographic examples that if you have an RG flow, the F at the UV fixed point is strictly greater than the F at the infrared point, and there's equality if you've got just a marginal deformation. There's very little evidence for the monotonic decrease. So as you perturb away, there's very little evidence simply because it's a hard calculation to actually do. Okay. And in fact, we have an example here that I'm about to tell you about where this monotonic decrease doesn't seem to be correct. So it seems that the strongest version of the F theorem is not quite correct, or there's something wrong with our holographic models. Okay, so if you want to do the change of F quantity under holographic RG flow, what do you do? Well, holographically, how you set it up is as follows. You take a domain rule solution where each slice is a sphere, and then the warp factor is basically telling you about the renormalization group flow. So you go from a value at infinity to a value in the deep interior of the space-time. And the domain wall is supported by a scalar. Now the scalar, as we said, you always need a scalar to be dual to an operator in the quantum field theory. The scalar is dual to the operator which is deforming the conformal field theory away from its fixed point. Okay, so the basic ingredient you need to describe a renormalization group flow is a warped metric where the warp factor is telling you how things change with renormalization scale, and a scalar field which is playing the role of the operator that deforms the theory. And so the mass of that scalar corresponds to the dimension of the operator that you're switching on. So what we did is we switched on a source for the operator, and we worked to quadratic order in this source. So we solved the Einstein equations to quadratic order in the source. If you only work to quadratic order, you're not sensitive to terms in the scalar potential of phi cubed and high. You actually only care about the mass. You won't see them, okay? And then we solved numerically to see what would happen. And we got a kind of a surprise. So what did we find? So let me explain the plot. So here is the dimension of the operator doing the deformation, and I show you in the plot things between 1.5 and 3, okay? So relevant is less than 3, and our bound is that delta is greater than d over 2, so delta is greater than 1.5 here. I'm not showing you what can happen for delta between 1 and 1.5 in this plot. Okay, now if we take a deformation where the mass is such that the delta ranges between 5/2 and 3, the change in the F quantity, which is the thing that's plotted over here, normalized by the Newton constant and the source squared, this is strictly negative. Okay, so that's what we expected. We said that F is meant to decrease when we do a relevant deformation of the theory. Okay, and so we've calculated, we switched on a perturbation, we worked to order a source squared, and we say, what is the change in F? And we say, okay, it's negative, so F decreased. But in the range of 3/2 to 5/2, the quantity is actually positive. It's scheme dependent at delta equals 5/2. That's because you get conformal anomalies there. That was actually related to the question the other day. So that I'm in 3 dimensions here. So delta equals 5/2 and delta equals 1/2 for the case which would give me conformal anomalies. If you're in 4 dimensions, your math terms would give you log terms as well. So you'd have finite terms. Okay, so the line here at 5/2 is simply meant to indicate that that will depend how I choose my scheme. It's something which will be scheme dependent. But away from delta equals 5/2, there is no scheme dependence. Okay, so this seems very strange. This seems that if we make deformations by operators in this range, the F quantity seems to increase along the RG flow. And again, whilst I haven't shown you the details of the calculation, all I'm doing here is just solving Einstein equations with a massive scalar field quadratic order in the source. I'm not sensitive to details of whatever potential the scalar actually has, you know, the cubic terms, because I'm only working to quadratic order in the source. So it seems a very generic phenomenon. So what's going on? So there's an analytic argument. So the first thing we thought was, okay, our numerics are kind of screwed up. But William is very good at numerics. That's why IBM want him. So it was not our numerics which were screwed up. There's an analytic argument for what's going on. So actually, in the range of masses between these 2 ranges, it's well known that there are 2 quantizations which are possible. And the 2 quantizations correspond to operators of 2 different dimensions. And if you follow the rules for the 2 quantizations, so the on-shell actions are related to each other by Legendre transformations. And so one can show on very general grounds that if for the delta plus operator, the delta plus quantization, the F increases, the delta minus quantization, it actually goes in the opposite direction. I.e., you know, if one is positive, the other is negative. If one is, you know, every time one is positive, the other one will be negative. Okay. This is just the rules for the Legendre transformation. And this is precisely what is going on here. Because if you look at this range, it isn't shown on my plot, but between 3/2 and 1/2, delta F was negative. Okay, and the 2 quantizations, so this is the delta plus quantization, and the thing that's not shown on the plot is the delta minus quantization. So we knew on analytic grounds that if one was positive, the other one had to be negative. And you could say, well, what happens if F2 is 0? But you know, we found that F2 was not 0 here, and you know, in generic grounds, it should not be 0. So it really came from the fact, it really came from these dual quantizations. This was our analytic argument. Okay, so either the delta plus quantization or the delta minus quantization must violate the strong F theorem. And it turns out that it's actually the higher value of delta that violates the strong F theorem. Now you say, okay, well maybe what happens in practice is that holographic theories which have a top-down realization only have one of the 2 quantizations. But that's not the case, because your probably favorite example of ADS4 CFT3 is the ABEJM theory, the Aharoni-Bergman-Jafferis-Moldacena theory, in which both quantizations certainly arise. Okay, so in that theory, you certainly have operators with ranges with dimensions in both quantizations. So our conclusion is either you find a reason why the flaw in the logic that these holographic flows are unphysical, and again I remind you I didn't use anything apart from the fact that free massive theories and standard ADS-CFT dictionary, or F doesn't decrease monotonically. So in our numerical flows, you can actually look at what happens in the deep interior, and they do seem to go to an infrared type fixed point in which the F at the infrared is strictly less than the F at the ultraviolet. So they satisfy the weaker version of the F theorem, but they don't seem to decrease monotonically.
What's the scenario in which they could be unphysical?
That is an open question to you, yeah. So many people at this point say, well, doesn't this contradict what people did in the literature? So the holographic cases that people explored in the literature, and I'm thinking of papers by Dan Friedman and Pufo and others, involve supersymmetric consistent truncations in which there were always more than one scalar present. So if you show me that you cannot have a consistent truncation with just one scalar here, because it's because we're on it's a Euclidean theory, so maybe we can, then that could be a case it's unphysical. But if that's the case, again, all I'm doing here is just Einstein gravity and a massive scalar field. I'm not taking potential terms. So if that's kind of screwed up, then all our bottom-up models are very vulnerable, right? Because we would usually say that's completely safe. If we start assuming things about potentials, then we say, okay, well, that might not be safe from a top-down construction, but I'm not assuming that. So that's the scenario. All the cases which people have consistent truncations of, say, n equals 8 supergravity, they've always kept pairs of scalars. And they evade what we found here because they've got pairs of scalars which compete against each other. So here I've just got one operator, right? One operator. In their case, they've got two, and they have to switch them on to keep, to be a consistent truncation. And the pair of them are such that they conspire, such that delta F is less than 0. They do have supersymmetry. And of course, in supersymmetric cases, one has other arguments that F is behaving monotonically. So it could be that you just can't do this in a supersymmetric theory, and that non-supersymmetric theories are perhaps in the swampland. But yeah, it's an open question. I mean, I've given this talk to a number of people, and nobody has found the flaw in the logic yet, including the usual Princeton, Harvard crowd. I mean, Cameron Vaffer is happy to say, he's happy to throw things in the swampland, but even he would rather throw the F theorem into the swampland here rather than this. Okay. Now, entanglement entropy. So if we play the same game with S, in fact, we did it the other way round, William and I. So we explored the renormalized entanglement entropy, and we noticed it wasn't changing monotonically along the flow. We again thought we'd done something wrong, so we went to calculate F directly. We went through the literature, and we thought it would have been calculated to quadratic order in the source. It hadn't. We discovered the problem with F. Okay, then we went back and said, no, there's nothing wrong with our calculation. It's simply the fact that the renormalized S, it directly matches what's happening with F. It doesn't change monotonically along the RG flow. But Cassini, Herter, and Myers always says this rather strongly, is that, well, who needs this F theorem from the Princeton group, huh? Because there is a natural monotonicity theorem for the renormalized entanglement entropy, or the entanglement entropy, which is a different version, which is that if you take the second gradient with respect to the radius of the region, this has a definite negativity property, and this follows from subadditivity of the entanglement entropy. So Myers' take on this is, well, who needs the F theorem from the Princeton group? Let's just work with this quantity instead, because we've got a nice sharp proof on it. Okay, so in my remaining sort of 10 minutes or 5 minutes or so, I'm just going to review the other sort of things I've been doing with entanglement. And then, obviously questions are welcome throughout, but these are things where if you want to know more, we can chat about them tomorrow or on Friday. Okay, so entanglement entropy, here I've been talking about doing this in sort of anti-de sitter, asymptotically anti-de sitter. But if you want to use entanglement entropy for sort of ADS CFT phenomenology, ADS CFT modeling, it's often considered important to go to a top-down string model, a 10-dimensional background. And that's for the issues that we were just discussing. So if you work with a 10-dimensional background that solves supergravity equations, you know that this is believed to have a consistent quantum field theory. If you just cook up, Einstein gravity randomly coupled to sort of scalar fields and potentials, you don't know for sure that this really has a proper QFT description. It might be kind of pathological, it might not really have a good description. So people, where they can, try to work with top-down models. I mean, often it might be too complicated, but they try to. And so one thing I did with Peter Jones, a former student who graduated this year, is look at entanglement entropy in top-down models. So the first thing we did was look at a computational model for entanglement entropy where you have probe brains in a top-down model. And so this built on work by Karch and his collaborators, where we allowed much more general probe brain embeddings with fluxes and so on it. And the second thing we did is that we proved directly that you can calculate the entanglement entropy using the minimal surfaces in 10 dimensions. So a very clean proof that you can actually do it with minimal surfaces in 10 dimensions. This is, I would say, somewhat non-trivial to really cleanly prove, but ultimately is really a version of the Lefkowitz-Moller-Senna proof. Okay, the other thing we did was with William is look at renormalized entanglement entropy in a range of holographic dualities that are not asymptotically ADS, but are non-conformal, but cases where we have a good understanding of what the dual quantum field theory is. So what I have in mind here is things like non-conformal brains. This is dualities based on brains which are DP brains, where P is not 3, where the dual quantum field theory is something which has dimensionally running coupling. Things like Schrödinger. So we looked at how you could do a renormalized entanglement entropy in those cases and what it captures. We also looked at how the finite part, this finite renormalized entanglement entropy, characterizes spontaneous versus explicit symmetry breaking. And the latter is interesting in the context, so people do, notwithstanding my complaint at the beginning that entanglement entropy in gauge theories is subtle, people do calculate entanglement entropy on the lattice. And actually understanding how to renormalize, as we've said here, and to see the signal of something being spontaneous versus explicit symmetry breaking is something that's actually quite useful for them. Okay. Now, there are many interesting measures of entanglement. So as I said at the beginning, I mean, people in the ADS community that has been doing condensed matter physics have been kind of using their condensed matter textbooks a lot to see, well, what phenomena would we like to reproduce? And people in this part of the community have been saying, well, there are many things in quantum information theory that we would like to do holographically. But in some sense, almost the punchline is that the quantum mechanical QFT measures of entanglement that people use, they define in quantum mechanical systems, they define in qubit systems, they define in QFTs, typically do not seem to be naturally realized geometrically in holography. So everything you can calculate in the quantum field theory must be able to be calculated somehow holographically, but it doesn't necessarily have to have a simple description. And so things like negativity, that's a measure of entanglement, is something that doesn't seem to be something which is realized naturally in terms of geometric quantities of the ADS spacetimes. And conversely, natural things geometrically, so why not take the volume of constant time surfaces, why not take partitions of ADS cross sphere spaces across the spheres? We've been talking about surfaces in ADS, but why don't we sort of think about cutting things across the spheres? Why not take Wheeler-DeWitt patches? Well, I don't think I myself would consider doing that, but of course people have been considering this recently. They've been thinking about natural geometric measures. It's very hard to match them with a QFT. And so in particular, the recent work on complexity is really about these two things here. And again, the punchline is that Firstly, it's very hard to define them cleanly, geometrically. Again, I'm happy to talk about this one in private, why it's so hard to define it. If you could do this one, you could essentially do asymptotically flat holography, in my opinion. So it's hard to define sharply, and it's also very hard to define what it is in a quantum field theory. So the proposal is that it has some relation to what people call complexity, which is essentially a measure of how close your state is to a particular kind of representative state. Okay, so a particularly simple state in the quantum field theory. It's very hard to measure them. So one of the things I was doing in this paper was exploring, well, amongst other things, was exploring whether there was a quantum field theory interpretation of taking an ADS cross S space-time and then cutting it across the sphere. Was there some kind of entanglement notion in the quantum field theory? And I think the summary was there probably is, but it's something which is incredibly unnatural, even more unnatural than the differential entropy, which many people here have been thinking about. Okay. So things which are in progress in various degrees of completion, which which I'm happy to talk about. So one thing I already mentioned is that we have a lot of results in the explicit computation of the renormalized entanglement entropy in free field quantum field theory examples. That's work with William Woodhead, which has been sort of sitting, it was in his thesis actually, and it just needs to be refined and put out. I should have said throughout actually, I was focusing on really static situations for my examples, that people are interested in entanglement entropy in time-dependent situations too. And in particular, renormalized entanglement plays a very natural role when you look at kind of quench type situations, so it makes things a lot cleaner there. I already mentioned I was doing something with Robin Graham, the mathematician. So entanglement entropy for regions with corners. This is relevant both because it hasn't been done in general in our community. So Rob Myers and co. did entanglement entropy for regions with corners in just pure ADS. But this doesn't capture all the geometric features. And it is this which would actually play a natural role in the mathematicians' the Wilmore conjectures, the generalizations of the Wilmore conjectures, and that's why Robin is interested in this. It's very interesting working with a mathematician as well. He actually calculates more than some mathematicians. The other thing is the first law of entanglement entropy. This is talking about the change of entanglement, how the change of entanglement entropy is related to the change in the modular Hamiltonian of the system. Both quantities are much more cleanly expressed using renormalized quantities. And so the proofs which were given by Monica Galka, Tom Hartman collaborators are much cleaner with renormalized quantities, and you can drop some of the assumptions and restrictions that they had. And that's something which the student, Linus, is doing. And the final thing is a renormalized definition of page entropy in the black hole context. So page entropy is when you've got the radiation coming out of a black hole, and when people discuss the information loss problem, actually I should almost have had a graph here. When people discuss the information loss problem, they do so in the language of the page entropy. So this is saying you have the radiation coming out of a black hole, and then it has an entanglement entropy. Now, if the evolution is unitary, you get a different answer for the page entropy, the evolution with time, than if the evolution is not unitary. So if it's unitary, then you should get all the information out of the black hole. So the entanglement entropy should go up with time, but then it should go back to zero, because at late time you should have all the information, and so the entanglement entropy is zero. The page entropy is zero. Whereas the original Hawking calculation would say that the entanglement entropy just goes up continually with time. But as Strominger pointed out a couple of years ago, we rely so much on this graph, and yet it's inherently ill-defined because entanglement entropy is divergent, right? So now we have a renormalized definition of entanglement entropy. Let's actually do this in the page entropy context. So let's actually sort of set it up there. But now you see the point is we're not defining entanglement entropy in terms of division of a Hilbert space spatially into two spatial regions. We've got a different division of the Hilbert space. So the logic is basically the same, but the partitioning of the Hilbert space is different in this context. So it's not a spatial partitioning, it's a different partition. But still the logic of the renormalization is the same. Okay, so final slide. I said I wasn't going to go to 6, but it's almost 6. Entanglement entropy can be computed holographically, and it can be renormalized both geometrically and in quantum field theory. I think it's useful. So if you want to do entanglement entropy for condensed matter and you're ultimately interested in systems which have a lattice cutoff, fine to work with a regulated quantity. If you're doing quantum field theory, which most of us are, then renormalized entanglement entropy is very useful. There are examples where doing things by background subtraction produced an ambiguous answer, but now with renormalization it's very clean. So examples there are some work by Carlos Nunez and Kobe Sonnenschein, where actually their answer was not clean and it becomes clean with this. And it's also useful for characterizing phases of the theory. So there's enormous progress. I mean, mine is just one sort of side corner, but there's of course a huge progress on understanding entanglement entropy in quantum field theory. Defining entanglement entropy in quantum gravity is still very hard, and I haven't touched upon it at all here. So what I'm getting at is these notions of quantum generalizations of the Ryuta-Kiyanagi, quantum versions of second law, and they're very hard to make very precise. Two sort of final questions. A criticism when I've given versions of this talk is, people say, well, I'm a high-energy physicist, I do QCD. Should I go and compute renormalized entanglement entropy? What would it be useful for? And I think that's still a very valid question. It is useful, computable for lattice theorists. So some of my lattice colleagues in Southampton, they can give arguments why they actually want to calculate and why it's useful in a lattice simulation. It's very far from obvious it's actually useful, computable in a QCD kind of context in general. Wilson loop computations, we have much more intuition what it's actually computing, right? So is this an interesting computable? It does capture phase information, but are there easier things to calculate? Probably there are. And the final question is, can you generalize what we've been doing here to quantum gravity? Can you do quantum versions and really make it, as I put, workable, that you can actually go beyond heuristics to actually calculate it? I'll stop there. I think that was the last.
Thank you very much. Is there a question?
I have one.
Yep.
About this July computation of the quantum terms, for Gauss-Bonnet gravity, can you do it for any value of the Gauss-Bonnet parameter? Or?
In principle, yes. Yeah, you can. This is a purely local computation, so it doesn't really depend on the global features of theory. Okay, so the answer is yes. Now, one thing I would say is that Gauss-Bonnet is of course harder because people have not found the counter terms for the action in a completely satisfactory way. And it becomes easier there if you constrain the parameters to special values, because then people have much cleaner results on the counter terms for the action. But in terms of the actual computation, those specific values of those parameters, they don't have a particular significance because we're always doing a local calculation for the counter terms. Yeah.
When you got to your work in progress, point 4 was about the first law of entanglement.
Yeah.
And I wasn't sure I got exactly what you do, I guess. Is it, you said that when you work with renormalized quantities, it becomes a lot easier.
No, well, not cleaner, because they had to make assumptions of certain fall-off of the fields in the bulk, and hence, they're making restrictions on the behavior of the stress tensor in the original proof.
That's what I was going to ask.
Yes.
I was talking about the relation with Einstein's equation.
Yes,
okay.
Yes, yeah. So we no longer need to make those restrictions that they make, so we can make a much more general proof than they're making. I should say this is a first-year student. I mean, I guess Ricardo's not met him. It's a sort of nice, straightforward calculation, but I think one which should be done because it's much cleaner. So, where they had to make assumptions of fall-off behavior so that they wouldn't get additional divergences in their entanglement entropy or in their stress tensor, we don't need to make those assumptions because we can just deal with them by renormalization. Yeah.
corners is related with the Gauss anomalous elimination in some sense?
Well, that is, of course, the interesting question. Yes, it is. So, of course, the very closely related calculation of the Null-Wilson loop done by Alday and Moldesano, that is, of course, directly related to the cusp, but in this case, where we have corners, one sees a very similar calculation arising, but we do not understand that the sort of the structure of the logarithmic terms in this case. If our region is a sort of a curved region, so we've got a corner, but our kind of background is curved. There's a geometric structure there which has not been explored. So it's probably got more information, not less. Yeah, it's got that information, but it's got more in it as well. Yeah. And actually, I should say I have interest in 3 for a long-standing issue of wanting to understand aspects of the Alday-Moldesano calculation, so aspects of how strings pinch off a cusp as they approach the conformal boundary. So there's another. I see that as a stepping stone to another calculation. But Robin Graham sees it as a stepping stone to a mathematical proof, so we're going more in that direction.
Let me also have one generic question. I don't know if even the question makes sense. When you discussed how you could see whether within holographic renormalization you have scheme dependence, and in particular whether you can have this finite piece or not. I'm trying to see if I'm thinking about this correctly, but if well, I mean, within holographic renormalization, you can see what possible variation you could have for terms that are scheme dependent. But is that to say that I guess, should I think of that as just one particular class of renormalization schemes within the field theory viewpoint? And if you renormalize some other way, which perhaps would be more natural in the field theory language, you could get something entirely different? Or
no,
if you cover all of the...
Yes, it does span. So if you don't find scheme dependence, you would not in general expect to find scheme dependence in another renormalization scheme. So one can go back to the QFT literature and see that discussed in a lot of detail. So zeta function versus dimensional regularization, if one doesn't have scheme dependence, you would not expect to find it in the other. Now, if you're asking about axiomatic quantum field theory, how good are the proofs, that I don't know. But at least there are proofs understanding in the standard quantum field theory literature that this is the case. And we're mirroring what's going on in the quantum field theory.
Yeah. No, I guess I was more curious about the case with scheme dependence. Is there something, I mean, within the range of answers that you get with scheme dependence within holographic renormalization,
would it
is there
span
something
on?
that we could be missing if we went to some other?
We don't think so. And okay, Costas would claim he's proved that there isn't. Again, you can decide how much you like his proofs. But it was discussed, I think, particularly in the work with Yanis Papadimitriou in the sort of 2005 papers. That was discussed in some detail. Yeah. You can criticize again.
Well, thank you very much. And we'll meet tomorrow at 4.